Okay, so good morning everyone. I am Amit. I will be talking about spatio-temporal spread of perturbation in a driven dissipative duffing chain using an OTOC approach. This work has been jointly done with Professor Anupam Kundu and Professor Manesh Kulkarni here at ICTS. So let's start with classical chaotic systems. So we can have systems with a very few degrees of freedom, for example a single duffing oscillator or a single Van der Pol oscillator, where there are many tools to analyze them like bifurcation diagrams, phase space portraits, Lyapunov exponent and so on. But if we go to the systems with many degrees of freedom, there are less number of tools to analyze them. There are some tools like this entropy potential, convective Lyapunov spectrum, but still people are in search of finding a good spatio-temporal measure to have a measure of chaos in classical extended systems. Whereas on the other hand, for quantum many-body systems, regarding scrambling of information and chaos, we have a very convenient measure called out-of-time order commutators, which basically measures the generation of non-commutativity in space-time of initially commuting operators. So a natural question to ask is that, is there some classical analog of out-of-time ordered commutators that could be a good spatio-temporal diagnostic in classical many-body systems? So indeed there are some recent developments in this direction. So out-of-time ordered correlates are identified in some classical many-body systems like classical Heisenberg spin chain, classical interacting spins on Kagome lattice and thermalized fluid, obeying implicit Burgers equation. But the point is that all of these classical many-body systems are Hamiltonian in nature. So the question we are going to pose is that, can OTOC be incorporated as a proper spatio-temporal diagnostic if there is drive and dissipation also present in the system? So to answer this question, as a model, we consider the driven dissipative chain of coupled duffing oscillators. The equation of motion is like this, where each of the oscillator is subjected to a individual double well potential, there is nearest neighbor harmonic coupling, there is a periodic drive, and there is dissipation. So with a simple suitable variable transformation, we can get to this equation. So ultimately the control parameters of the system are like scaled versions of the dissipation, coupling, drive, driving amplitude and driving frequency. So now the question is how to define a OTOC like spatio-temporal measure for this kind of systems. Yeah. Sorry? This one? Oh, this is actually suffixed, this yi plus 1 suffixed. I plus 1. Yeah, yi plus 1 suffixed. Displacement of the oscillator before that. So how to define OTOC like quantities for this kind of system, driven dissipative system? So we consider two almost identical copies of the duffing chain at time t equals to 0. So by almost we mean that there is an infinitesimal deviation in the initial conditions at the middle oscillator. And the question is how that initially localized perturbation spreads to the other oscillators in space at some later time. So to measure this, we define this kind of quantity d, which is a function of space and time. So this is a ratio of these two quantities, where the denominator is the initially localized perturbation at the middle oscillator, and the numerator is the perturbation which is gained at some other oscillator I at a later time tau. So this quantity can be numerically calculated easily from the equations of motion with this kind of initial conditions. So now, as we have defined a spatio-temporal measure in a classical many-body system, so let's try to see how the space-time diagrams of these quantities infer information about the dynamics of the driven dissipative duffing chain. This is our one of the main observations, where I see that these are the OTOC heat maps, where the x-axis is the I and y-axis is the time tau. So we see there are three different dynamical regimes in the duffing chain. So one is sustained chaos, one is non-chaotic regime, and one is transient chaos. So in case of sustained chaos, what happens is that the initially localized perturbation spreads ballistically in space and also grows in time indefinitely. So this growth sustains in time, so it is called sustained chaos. Whereas in contrast, in case of non-chaotic regime, what happens is that there is no growth of the perturbation, rather it decays, and there is a initial ballistic spreads, but this light conformation ultimately vanishes with time. Interestingly, for transient chaos, what happens is that initially we have a light conformation in both these curves. This is like the chaotic thing, but in both of these curves you can see that at some point there is a sudden change of the slope. So what happens is that initial light cone ultimately deforms to some complex geometric shape. So in case of transient chaos, we have complex geometric shapes with initial light conformation. So now since this transient chaos thing is most interesting, so let us try to describe this transient chaos thing. So before that, what we try to do is to extract some quantities from the OTOC which separately measure the spatial spread of the perturbation and the temporal growth or decay of the perturbation. So for spatial spread, we define this instantaneous speed kind of quantity. If you see the numerator, what is measured basically is the number of oscillator which have gained a perturbation which is greater than or equals to dth times the initial perturbation epsilon. Okay. Whereas this finite time Lyapunov exponent basically measures the growth or decay of perturbation with time, and there is another quantity which is called velocity dependent Lyapunov exponent, which basically measures the growth or decay of perturbation as one moves with a velocity v with respect to the initially perturbed oscillator. Okay. So let us first consider the most interesting regime, which is the transient chaos. This is a particular choice of parameters which gives a transient chaos regime. So this is again, we have plotted the boundaries of the heat map which we have already shown. So there we can divide this region into three time intervals. One is tau less than tau star, one is tau is between tau star and tau tilde, and another is when tau is greater than tau tilde. So what happens in this first region is that the system behaves chaotically. This is this initial light conformation which we have also seen in case of sustained chaos, and this thing is independent of the value of the DTH. So these different curves correspond to the different values of the threshold DTH. So this initial light after this initial light conformation, we see that there is a sudden change of slope, and this change of slope can also be observed from the Lyapunov exponent as a function of time curve. So here also we see that when tau is less than tau star, we have some oscillators which have gained positive Lyapunov exponent, but at this particular point when we have reached tau star, the Lyapunov exponent of all these oscillators start decreasing simultaneously. And this second time tau tilde is the point at which the perturbation stops spreading. So after this point, for a particular value of DTH, the perturbation does not spread anymore. So this in the FTLE plot means that the oscillator which have just the farthest oscillator whose Lyapunov is positive starts decreasing and goes down below 0. So in terms of Lyapunov exponent, what happens is there are some oscillators which cross the Lyapunov 0 twice. That is, it first goes from negative to positive. At some particular point, all the Lyapunov, all the oscillators start decreasing simultaneously, and then they go below 0. Now we have shown two different transient chaos plots. This is the second one. So what we will describe here that at later time in the transient chaos regime, what happens is that although each of the oscillator has its own double well potential, what happens is that each oscillator gets stuck at the minima of a single well. So at that point, this Duffing chain can be approximated by a Divine dissipative harmonic chain. Okay. so there is two figures. One is where we have simulated the Duffing chain directly, and there is another one where we have made a harmonic approximation at later time. And we see that these two curves matches quite well. And when in this transient chaos regime or non-chaotic regime, the Duffing chain can be approximated by a harmonic chain. Since the harmonic chain is a linear equation, we can analytically solve this chain, and we can have expressions for OTOC, the velocity dependent Lyapunov exponent, as well as the butterfly's velocity with which the information spreads in space. Now, let us describe the other two regions also. So, what happens in case of sustained chaos is that these boundaries are independent of the threshold value DTH, and the slope of this boundary, which is basically the butterfly speed, can be computed from the equation I have shown you, and so this goes to some constant butterfly speed with time. So, we see a ballistic spread which is independent of the threshold and a constant butterfly speed. This constant butterfly speed can also be measured from the velocity dependent Lyapunov exponent curve, where basically this butterfly speed is the zero of the velocity dependent Lyapunov exponent. And from the Lyapunov exponent versus tau curve, what we see that in case of transient chaos, what we observe is that the oscillators cross the Lyapunov zero twice. But here what happens is in case of sustained chaos that the oscillators cross the Lyapunov zero once and saturate to some positive constant. Whereas in contrast for the non-chaotic regime, what happens is that these boundaries are very much dependent on the threshold value. So we have a ballistic speed only in the limit when this threshold goes to 0, and only in this DTH goes to 0 limit we can define some kind of constant butterfly velocity. And from the FTLE curve, what we see is that this doesn't cross the Lyapunov 0 1. The number of times it crosses Lyapunov 0 is 0, and so let us just briefly summarize. So OTOC provides a clear description of the three different dynamical regimes of the different dissipative Duffing chain, which is sustained chaos, non-chaotic regime, and transient chaos. And we can also derive the tools directly from OTOC for spatial spread and temporal growth, which are the instantaneous speed, FTLE, and velocity dependent Lyapunov exponent. And we can demarcate between the three different dynamical regimes directly from this quantity, that is crossing of Lyapunov 0, which is n equals to 1, 0, 2 for sustained chaos, non-chaotic regime, and transient chaos respectively. And in the non-chaotic regime or at the later time transient chaos regime, the system can be approximated by a harmonic chain. So yeah, so that's, thank you.
Questions?
Like what is the usual just response function in this system? Like if you look at correlations or something, like the linear just linear response, is it diffusive or ballistic?
Yeah, like the what is the question?
If you just look at response at linear according to linear response,
yeah,
then is it like diffusive spreading or ballistic, or I mean probably there's no conserved quantity, right? In
no,
system.
this is a
But so but you can still ask for response. I mean
it's probably not exactly diffusive. So if you see this so this curve, so for there is this lambda v as a function of v. We have seen an exponent like 2 in some kind of Hamiltonian system, for example Heisenberg's spin chain, where there is a Hamiltonian some conserved quantity. But in this case we don't see this diffusive behavior like this exponent 2. It is actually fitted by a different curve. So
for Hamiltonian this is 1, right? I guess.
Yeah, near v equals to vb it's 1, but as you go like far from v equals to vb, it is actually 1 minus v by vb square for Hamiltonian systems. But here you observe different kind of different exponents, and actually the whole curve can be fitted by, like, if we add some v plus v by vb to the power 4 term something.
Can you go to the slide where you showed this ballistic?
Yeah.
Yeah, this one. So I'm just trying to, so first of all, what are the color bars? What do the colors represent?
Yeah, so this is a measure of this quantity.
Right, so
So
it's
this is the initial perturbation, and this is the perturbation which is gained at some different oscillator at later point of time. So what happens is that this is the initial perturbation created at the middle oscillator. This spreads ballistically in space and it grows also.
Okay. Okay. So second thing is in that plot, in the non-chaotic regime plot, why is it only, so it has a directional preference to the vertical or the 45-degree lines? Or, am I wrong?
So actually here the initial the perturbation doesn't grow. So what happens is that only the middle oscillator has this perturbation epsilon, which is the initial perturbation,
yes.
which has the highest value.
Sure.
The perturbation spreads, but the value is less than epsilon. So
Okay.
this is higher than the the perturbation here is higher than the other points.
No, that is fine. But for example, what about the 45-degree lines? Why? So because I see
This thing?
I mean, I would have expected, I mean, just naively, I would have expected that it should be some sort of uniformly dying sort of thing, right?
So you were saying about this
Yeah.
this thing?
Yeah.
Yeah, this is the with some velocity it spreads, right? So if you see this quantity, so this is basically the number of oscillators. This slope will change. So let's go to this curve. So you are asking about the color bar, the maximum of the color bar. So this is the threshold actually. If you change this threshold, means the how many oscillators have gained a perturbation say 1, or how many oscillators say have gained the perturbation 10 to the minus 2. Depending on that, this slope changes actually. So this angle changes. Yeah.
Okay. Thanks.
Let us thank this speaker.